Hello and welcome again. This is DB93. This video is to discuss the idea of conservation of mass in terms of a video that Peter and Pete have done. Now, it's actually the first video of theirs that I saw, and the reason I saw it is my brother linked me to it because apparently one of the followers was saying that they stumped a chemical engineer with the question. Being a chemical engineer, I was interested. I had a look and I said I knew exactly what was going on. Didn't stop me at all. And one of the easiest ways to disprove the claim is through the calculation of conservation of mass. Now, for those of you who haven't seen the video, basically they call up a company that make what are called HHO devices. This particular device used deionized water and a potassium hydroxide electrolyte to electrolyze the liquid and make hydrogen oxygen gas, which it then mixed with a booster to make a blowtorch, mainly for jewellery, as far as I can tell. So I thought I'd come up with a quick sort of example, and I may at a later date actually call up the company or contact them and see how much they do put in and see if they can actually do the test, which I'll recommend at the end of this. But for now, we'll just talk about the conservation of mass, and we'll do some maths around it too. And before I get started, it is very important that you know what the mole is. It's a unit, and it's a unit of quantity. Now, what I mean by that is the mole, which is spelled MOL, is equivalent, so 1 mole is equal to Avogadro's number, which is 6.022 times 10 to the 23 items of whatever. It's a count, like a head count. So for example, you could have 1 mole of bananas, which would be 6.022 times 10 to 23 bananas, and that's a bloody lot of bananas. So what this power, if you're not familiar with mathematics, 1 million is equal to 1 times 10 to the 6, because 1 million has 6 zeros trailing that 1. So 1 to the 23 would be 1 followed by 23 zeros. So it is a very big number. All right. Now, if you had 1 mole of bananas, you'd have 6.022 times 10 to the 23 bananas. If you had 1 mole of feathers, you'd have that same number of feathers. Now, the 1 mole of bananas weigh a lot more than 1 mole of feathers. Likewise, 1 mole of feathers would take up less space than 1 mole of bananas because you can pack them down. So all this really does is the mole is a link between mass and units, and it allows us, so nearly all chemical equations navigate via moles, and then you then convert from moles into the units that you want. Okay? Now, for those of you who aren't familiar, potassium hydroxide is KOH. So it's a potassium atom bonded to 1 oxygen and 1 hydrogen. Or actually, I believe it's bonded to 1 oxygen, and that oxygen is bonded to a hydrogen, I think. I can't tell from memory, I'd have to look it up. Either way, that's your molecular formula. Now, the molecular weight is the sum of the atomic weights of the 3 atoms in the molecule. So we have potassium, which is 36.1. Sorry, 36.1. And that's grams per mole. So 1 mole would weigh this amount. Oxygen is equal to 16 grams per mole, and hydrogen is equal to 1 grams per mole. So your molecular weight is equal to the sum of these. So 36.1 plus 16 plus 1 is equal to 56.1 grams per mole. Now, let's suppose you add 10 grams to 100 milliliters of water, so 10 grams of potassium hydroxide. we can then use what's called the mole equation to calculate how many moles 10 grams is. And the mole equation looks like this. So you got your moles, which is N, is equal to your mass by little m, divided by your molar mass, which is your big M. So in this case, 10 grams divided by 56.1 is equal to 0.178 moles. Now, in the same way as if you had 3 ping pong balls stuck together, and say one's red, one's green, one's blue, and you had 1 mole of them. If you wanted to count the individual colours that were in that grouping of the whole mass of it, that mass of 1 mole of groupings would be 1 mole of green, 1 mole of red, 1 mole of blue. Okay? So we can then use that to determine how much oxygen, how much hydrogen are in the system. So your moles of oxygen atoms is equal to 0.178, and your mole of hydrogen atoms is equal to 0.178 as well. Now, presumably it comes out in a stable form, stable gaseous form, which is O2 gas and H2 gas. Now, in the same way as if you got 14 ping pong balls and you pair them up, you end up with 7 pairs. You halve the number. So we'll halve this number here because we paired these up, and you get 0.089 moles and 0.089 moles. And so the total amount of oxygen and hydrogen gas coming out, so the sum of these two, we add them together, is 0.178 moles coming out of the end there. Now, we could convert that back to mass, but as you probably guessed by now, it's hard to measure the mass of gas, especially when some of the gases are lighter than air. So, thankfully, we've got what's called the standard gas equation. And that looks like this. Pressure times volume is equal to the mole multiplied by the gas constant, R, multiplied by the temperature. Now, this relates pressure and volume and temperature into terms that we can then convert and understand. Now, we'll make assumptions based on what the other variables are. So, for instance, we'll assume that it's at standard laboratory conditions, which is 21 degrees Celsius, which is, T is equal to, which is 294 Kelvin, which is your standard scientific notation for temperature. A lot of equations work that way. Your pressure is equal to 1 atmosphere, which is equal to 101,325 pascals. And your gas constant R is equal to, I'm pretty sure from memory it was 8.314, and I'm not even going to bother with the units. But if you look up the gas constant, you need to be careful which units you use, because that'll change this number. So for this number, you need to use the units pascals, Kelvin, and the volume will be in meters cubed. Okay? So now we need to rearrange this equation here, and we need to do it in terms of volume. So that rearranges to be volume is equal to moles multiplied by the gas constant multiplied by the temperature divided by the pressure. Okay? Now, we can then add in our values here. So we got 0.178 multiplied by 8.314 multiplied by 294 over 101,325. Okay. Now that works out. From here it won't be quite as accurate because I think in my calculations I got the 3 and the 4 mixed up. So it'll be a little bit different, but not much, because consider it 1/10 of a decimal compared to 294. You know, it's not a lot. So it'll be roughly right. And I'm sure I'll add in little captions into the video with the correct calculations as I go. But the calculations I did get was that the volume is equal to 0.0043 meters cubed, which is equal to 4.3 liters. Now, just for reference, a standard balloon volume is equal to 0.015 meters cubed, which is equal to 15 liters. Okay, so one of the experiments I'm going to talk to this company about and see if they can actually do this and provide the video for it to me. Or if you've got a unit at home, I would really appreciate it if you tried this and then sent me the video. But what you should be able to do is, if you put 10 grams of potassium hydroxide in your HHO unit, assuming P&P weren't correct, you'll only be able to fill it about a third of its potential volume. You definitely wouldn't be able to fill it up to its full volume or burst it. Now, if they can do this and they can burst the balloon, then it proves that P&P were wrong and that the electrolyte is not the only source consumed. The potassium hydroxide cannot be the source being consumed, it must be the water. So I thought I'd just give this to you guys, food for thought. Let me know in the description if you agree with any of this, if you think any of it is incorrect or wrong. Or if it doesn't make sense and you've got questions, ask away. All right? Catch you later.